In the last class, we looked at the fact that as acids become weaker, their conjugate base becomes stronger, and vice versa. We determine the strengths of weak acids by using the Ka value, and determine the strength of weak bases using the Kb, which you can calculate from the Ka. What we did not show was where those Ka values come from. We don't use the Ka value for strong acids and bases because they dissociate 100%. But we use the Ka and Kb values for weak ones because that's how we tell how strong they are. And I want to show in the first problem how you go about calculating in the lab the Ka of a weak acid. You're going to have an experiment where you calculate Ka of a weak acid that's done by titration. The thing is, though, this is a very straightforward method of doing it, and I want to show you it's a little bit different than what you're going to do in the lab, but it's very instructive. All you really have to do to get the Ka of an acid in experimental circumstances is to dissolve a known amount of the acid in a known amount of water and measure the pH with a pH meter. Now, why in the world would you be able to get the Ka just from data like that? It doesn't sound like that much. The reason is that you know that as the Ka of an acid gets bigger, it gets to be stronger. The stronger the acid, the more H pluses it gives off, and so the pH goes down. That's the reason why you can relate the Ka to the pH, because the lower the pH, the larger the Ka will be. So there should be a way to do that mathematically. So I'm going to use the example of the weak acid phenol, which is very common in organic. It's used for synthesis and also for other things. If you dissolve 3.85 grams of the acid in 500 ml of water, you measure a pH of 5.49. I want to show you how you can use that information to get the Ka. Phenol is not in your table of Kas, but I could have put it in there. I just want to show you how you could get a number to put in the table if you wanted to. So the first thing you got to do is convert to molarity, because we got to do everything with molarity. So I took, first of all, the grams and divided by the molar mass to get moles, and then I divided moles divided by 0.5 liters to get molarity. So that's what we're going to start with in the ICE table. Now, even though we're using an ICE table just like we did the last class, the problem is different. It's actually kind of the reverse of what we did in class last time. So let me show you why that is. I showed you the initial row here, and you know you're going to shift towards the zeros, so the ICE table looks just like it did in the problems last class. You end up with the pluses and minuses the same, and so now you need to write the Ka. You write the Ka and plug in the x's, and you ignore the x relative to the original, and you get x squared divided by the original. Now, in the previous problems in class last time, what we would do is look up the number in the Ka table, set the fraction equal to that, and then solve for x. The thing is, for phenol, we don't have the Ka value. We're going to do exactly the reverse. We're going to first of all get x and then plug it in. The way you can get x is by measuring the H plus concentration, and you can do that from the pH I gave you in the problem. So the first thing I did was take the inverse log of negative 5.49, which is the formula for converting pH to H plus. That is also x in this problem, so all I have to do to get the Ka is plug it in. You can see that this number is very small, but I could put it in the Ka table for phenol if I wanted to. The thing is also, this, I hope you can see that this is really the reverse of last time. We didn't look up the Ka and sulfur X. Rather, we used the pH to get X and then plugged it in. This is another example of the problem with a different acid, and I wanted to do this because I want you to have two of these in your notes, but I also want to review some of the things that we did in the last class. This is a good way to do it. I picked this acid, cacodyllic acid. It's one of a couple hundred of them that are listed in the Handbook of Chemistry and Physics, and it has arsenic in it, which is kind of cool because that's poison. But the thing is, what the problem says is that if you dissolve 2.07 grams of it in 250 ml of water, this acid will give you a pH of 3.71. And from that you can get the Ka. The question is, what does that pH that's lower than the previous problem mean about this acid? Well, if this acid has a lower pH, that means that it's giving you more H pluses. Since it's giving you more H pluses, it's also stronger than the previous acid, and so it should have a larger Ka. So let's calculate it and see if it really does. I took the moles again. I took the grams again and converted to moles, divided by the molar mass, divided by liters and got molarity. Made the ice table just like we did last time. Plug in the x's, ignore x relative to the original, get x squared over the original, and now we need to calculate the x again. Take the inverse log of the negative pH, and you get a number that's larger than the H plus from the last acid. When you plug it in for the x and square it, you get a Ka value that is larger than the previous one. The previous one was 10 to the minus 10. This one's 10 to the minus 7. So it is a stronger acid, gives you more H pluses, so it gives you a lower pH. So everything fits. Now, we could have done that problem last class, but we already did enough in that one class. But we calculated the pH of diprotic acids during that class. What I showed you is that for a diprotic acid, if you want to calculate the pH of it, all you have to do is use only the first step with the Ka from that step and do an ordinary weak acid problem just like you do with any other weak acid. This was the example from last class that when we calculated the pH of carbonic acid, we ignored the second step and used only the first. And this is the calculations we did. And you end up with the final answer in the percent ionization. So we concluded that if you're calculating the pH of a diprotic acid, you use only the first step and ignore the second one. Today, though, I want to use an example of calculating not the pH, because that's only one thing that's of interest. The other thing that chemists want to calculate is the concentration of the -2 ion that comes from the acid in the second step. The reason why chemists want to do this is that they like to use -2 ions to precipitate things in the lab. Because as I'm going to show you, it's very easy to manipulate the concentration of the A2- so that you can make it anything you want for the purpose of precipitating. The thing is, you have to know the concentration of this ion if you want to do will it precipitate form problems, because you have to plug in the number in the Q value. In the first lab that you do, you're going to precipitate calcium carbonate, and that uses CO3 2-, which actually comes from carbonic acid, as the precipitating agent. And so in the very first lab, you're using this concept to precipitate. And there's where the CO3 2- comes from. It's in the second step. If we're going to be able to do will precipitate form problems where you precipitate carbonates, we're going to have to calculate the concentration of the carbonate. The first kind of calculation is to calculate the concentration in pure water. So if you look, though, at these two steps, you remember that the first step is always much stronger than the second step. And so the first step splits apart 1-to-1 into H plus and HA minus. The second step is very weak, and so the HA minus is not going to split apart much more. So you can assume that the concentration of H plus and HA are going to be equal throughout the experiment. The thing is, A2- is not in the first equation, and so you're going to have to write the Ka expression for the second step, not the first one. So if I use the second step and put products over reactants, this is what it looks like. The thing is since the H plus and the HA are equal, we can cancel them. There it is done. And so what we end up with is that the concentration of the -2 ion is actually just equal to the Ka2 value in the table. The thing about this is that it doesn't matter how much H2A you use, because adding more H2A is not going to change the fact that the H plus and the HA are equal. So you can't increase the amount of A2- by increasing the amount of H2A. You have to do it a different way. But in order to find the A2- in pure water, it's very easy because all you have to do is look it up. I wrote this on the top of the next page that for any diprotic acid, H2A at any concentration, the concentration of the -2 ion equals the Ka2 if the acid is dissolved in pure water. What that means is you didn't add anything. You didn't make the solution more basic or more acidic or anything else. You just dissolved the acid in pure water. This is the kind of a problem you get about this. What is the concentration of SO3 2- in really any concentration of H2SO3 solution? The hardest thing for people about this is recognizing what kind of a problem it is, because it's one of the easiest ones we do. All you have to do is look it up. So let's find it. Sulfurous acid is not the strong one. That's sulfuric. So sulfurous acid is on the very bottom of page 10. It has the two steps, and it's weak. I made the equations bigger so you could see them here. How are we going to find the concentration of the SO3 2- then? The calculation we just showed is that if H2SO3 is in pure water, the concentration of the SO3 2- is just the Ka2, and all you have to do is put molar after it. So all you're really doing is looking it up. It seems too easy initially, so you just be able to look up the answer. But what I want to show you is that this number can be controlled by using the pH. So what if that concentration of A2- is not enough to precipitate an ion that you want to precipitate? We already said you can't increase the amount of that -2 ion by using more H2A, because the H plus and the HA- always cancel. But you can increase it by changing the pH. Even though we're not doing precipitations with H2S in the lab this semester because you're doing them at home, This is an important enough system in chemistry that I want to show it to you. People use H2S, the diprotic acid, to precipitate what's called the group 3 ions, which includes the top row of the transition elements. And they also use H2S to precipitate the tin and copper ions, along with a lot of other ones that are also precipitate with S2 minus. If you look at how much S2 minus there would be in pure water, it would be very, very little, because the Ka2 is weaker than water, and the S2 minus would be equal to that number. Whatever it is, we can't calculate it because it's weaker than water, so nobody knows for sure what it is. But the idea is that for the ions in group 3, shown above here, the concentration of S2 minus in pure water is not enough. And so what you can do is you can make the solution basic. You increase the pH, which is equivalent to adding OH. And if you eat the H pluses by making water, you shift to the right, which increases the concentration of S2 minus. And that allows it to be high enough to be able to precipitate the group 3 ions. If you wanted to precipitate the ions that are in group 2, you would add H plus and make the solution more acidic, and then you would shift away from the S2 minus, and that would make it even smaller than it already is. That's the basis of how you separate group 2 and 3 in the lab. So for the questions I ask about diprotic acids, I only want you to know those two things at the bottom of this page. If you're calculating the pH, you use only the first step and you do a weak acid problem. If you're asked for the -2 ion, you just look up the Ka2. I could show you an equation where you can calculate the new concentration of the -2 ion at different pHs, but I'm not going to do that. Nobody really knows the Ka2 of H2S, and that's the one you're the most interested in. So I just wanted to show you the principle without actually doing calculations. This is the main subject of the first half of class in this lecture. Last class, we calculated the pH of strong and weak acids, including diprotic acids, and strong and weak bases. In this class, I want to calculate the pH of salts. But if you look at these, you might not even think that salts would be something that would have a different pH. What's the definition of a salt? If you remember what we said, a salt is really any ionic compound. A metal ion plus any negative ion except OH, if it's OH, that makes it a base. You might not think that these would even change the pH because they're a salt. They're not either an acid or a base. But I want to show you some evidence that they do change the pH. I can give you the following results, that when you dissolve salts, the pH can either become more acidic, more basic, or stay unchanged depending on what the salt is. If you take the pH of a solution and then dissolve some table salt, sodium chloride, the pH does not change. Sodium chloride is what's called a neutral salt. But if you dissolve the salt potassium cyanide in water, it gives you a basic solution. And so this one is what's called a basic salt. And if you dissolve ammonium nitrate in water, you will get an acidic salt, and so an acidic solution. It's called an acidic salt. We need to explain this, and in order to do that, you have to realize that when these things dissolve in water, they don't stay together, they become ions. And so what we want to do first is look at what do positive and negative ions do to the pH of a solution. There's 4 classes of ions that I'm going to describe. It's not very difficult to figure out what they are. There are positive ions that affect the pH and positive ones that don't. And there are negative ions that affect the pH and negative ones that don't. The first class that I want to talk about is what are called neutral cations. These are positive ions, but it sounds like a kind of a weird thing because the word neutral oftentimes means no charge, right? So how can you have positive ions with no charge? Well, the answer is that the word neutral in chemistry has two different meanings. Neutral, as it can mean no charge, but the other meaning is pH neutral. In other words, it stays at pH 7. So that's what we're talking about. These are positive ions that do not change the pH. All I'm going to tell you about these is that the ones that are like this, that are the most classic ones, are any of the metal ions that come from either group 1 or 2 in the periodic table, do not react with H2O, and they don't change the pH. If you look at what's in these two groups, there are a lot of important ions, especially medical ones. Sodium and potassium and magnesium and calcium. None of those four ions change the pH of a solution that they're in. You can show that by just saying no reaction if you put them in water or putting a double line through the arrow. It just means that they get surrounded by water, but they don't do anything, so they retain neutral pH. And these are some of the examples from the table. There is one positive ion, though, that does affect the pH that I want you to know. We talked about extensively last class that the ion ammonium, NH4+, is a weak acid, and therefore it's an acidic cation. Any compound with ammonium in it will tend to be acidic. Ammonium is on the left of the arrows in the Ka table, and therefore it's a weak acid. The reason it's acidic is that when you put it in water, it breaks apart to give up H+, and that makes the solution acidic. There are some ions in the transition elements that are acidic also. For example, iron 3 and copper 2 are acidic. The reason they're acidic, though, is advanced inorganic chemistry, and you have to know about metal ion complexes, which we haven't done yet. So I really don't want to cover those. The only one that changes the pH that I want you to know is ammonium, which is an acidic cation, and it's a polyatomic ion, not an element. There is no such a thing as a positive ion, though, that's a base. Bases accept H+. According to the Bronsted theory, positive ions would repel H+, and so there's no positive ions that are bases which it would and they won't accept H+. There's also a class of negative ions that do not affect the pH called neutral anions. I'm going to define these as negative ions that come from strong acids when the H+ is removed. Those are the ones that we call the conjugate bases of the strong acids, because if you look at that table from last time, we said that those negative ions are so weak of bases, you have to put them in an organic solvent in order to even see that they're bases. They do not act as bases in water, and so they don't change the pH. I showed that for Cl- and NO3, which both come from strong acids, HCl and HNO3. Since there are 6 strong acids, there should be 6 of these ions. I showed them, but the thing is, you don't include HSO4- because it's true that it's not a base, but it's not neutral either, because it can give up an H. It's actually an acid. So we're going to discuss that one separately. But the other negative ions listed there are neutral anions. So there's 5 of these, the ones that are in boxes here. So this class only has 5 ions, but they're very important ions. There's also a class called basic anions. The reason these are basic is because they come from weak acids when the H plus is removed. These are the ones that react with water to produce OH minus, and these are also the ones that are on the right of the arrows in the Ka table. All these ones we looked at last time. We said that these are all weak bases. And they also include the -2 and -3 ions that don't have any H's still attached to them in the polyprotic acids. As I showed here, which we already talked about last class, the reason why these are bases is because they pull an H off of water partially to produce OH. I listed some of these from the table. These are not the only ones. All the ones that you can find on the right of the arrows in the table are basic. There is a class, though, that we haven't talked about yet, which we do have to deal with, and those are what are called amphiprotic ions. If you look at bicarbonate, which I showed you here, the bicarbonate ion can both give up an H+. That's the first reaction where it's acting as an acid. It can also, though, accept an H+ from water and produce OH, and that is the second reaction that's here. The reason it can do this is because it's possible for it to either give up or gain an H+. These are what are called amphiprotic ions. All the ones that are in boxes here in the diprotic and triprotic acid table are amphiprotic. They're the ones in the middle that still have some of the H's attached, because in the top equation they can act as a base, but in the second equation they can act as an acid. The exception to that, of course, is HSO4- again. HSO4- is not specifically amphiprotic because it cannot react with water to take away an H. Sulfuric acid is a strong acid, and so HSO4 is always 100% separated from H+, but it can act as an acid. If I was going to make a class out of this, I would have to call it an acidic anion, but I don't want to do that because it would be the only one, and I think it would be kind of confusing. So we're going to always talk about HSO4 separately. By far, the most important amphiprotic substance on Earth is water itself. Water, as you can see, can give up an H+ and act as an acid. It can also pick up an H+ and act as a base when it makes H3O+. I told you earlier that I think the main word in biology that you could summarize it with is homeostasis. And homeostasis depends on buffers. You can show that if the solvent water were not amphiprotic, we would not be able to have any of the buffers that exist, and therefore life on Earth as we know it would not exist. It's necessary to be able to have a solvent that will keep the pH constant. And because water is amphiprotic, it works for that purpose. Okay, now that we've defined the 4 types of ions, not including amphiprotic ones, we want to make salts. And the first kind of a salt I want to make is a neutral salt. I have type numbers on each one of these, but you don't have to know the type numbers. The only reason why I use types is to classify things so we can talk about them, but those are not required to know. But I'm calling this type 1, which is a neutral salt. If you take a neutral cation and combine it with a neutral anion, you're going to get a neutral salt. As we said, the neutral cations are the ones that come from groups 1 and 2 in the periodic table, And the neutral anions come from strong acids. So the neutral cations are here in group 1 and 2, and the neutral anions are at the bottom of the page in boxes. They come from strong acids. So when you put two of these ions together, you get a salt that cannot change the pH. And here's some examples. Question is, why is sodium chloride neutral? Because when it dissolves in water, it splits apart 100% into ions. Sodium cannot react with water, and neither can chloride, and therefore there's nothing to change the pH. So you put neutral and neutral together, you get a neutral salt. If you want to make an acidic salt, what you're going to do is put together an acidic cation with a neutral anion. The only acidic cation I want you to be familiar with is ammonium, and so that's the one you would start with, and then you would put with it one of those anions that comes from a strong acid. And here's the 5 ions that are neutral. So there's only really 5 of these compounds that we would talk about, and I showed you 3 examples of them here. The reason why, for example, ammonium nitrate is acidic is when it splits into ions, 100%, because ammonium makes everything soluble. The ammonium gives off H pluses, which tends to make the solution acidic. NO3 is neutral. And so if you put together an acidic and a neutral, you get an acidic salt. You can make a basic salt by putting a neutral cation with a basic anion. The neutral cations are the ones that come from groups 1 and 2. The basic anions could be any of the ones on the right of the arrows in the Ka table. And here are the neutral cations again. The basic anions are the negatives on the right of the arrows, including the ones that come from di and triprotic acids. I showed you examples of a few of these salts. I think the middle one, lithium carbonate, is really interesting because it's one of the mainline treatments for bipolar illness. Bipolar has probably to do with the sodium-potassium gradient across membranes. Lithium is a much smaller ion than those two, but it's still +1, so it can distribute itself pretty evenly across membranes because pores don't really block it. That probably has something to do with the mechanism of action, and they have many prescriptions of lithium carbonate are filled all the time. The reason why one of these salts, for example, potassium cyanide, is basic, when it splits apart into ions 100%, the K is neutral, so it can't change the pH, but the cyanide is a basic anion, so it pulls an H off the water and gives you OH. So if you put together a neutral and a basic, you get a basic salt. There is a salt that's called a mixed salt, where you can put together an acidic cation and a basic anion. The thing is that we're not going to really look at these to calculate the pH of them, because the acidic one is trying to give you H's and the basic one is trying to give you OH's, and they're kind of fighting each other. You can do this problem by doing what they call simultaneous equilibrium in analytical chemistry, but I don't really want to do that because it's beyond the scope of our class. So I'm just going to show you examples of these. They exist, they're very important, but we're not going to actually calculate the pH of them. These would be formed if you took ammonium and put it with any of the ions on the right of the arrows in the Ka table. I showed you a few examples here. Ammonium acetate is used in buffers all the time, and ammonium carbonate is a very important precipitating agent. So these kind of salts exist. We're just not going to deal with them, but we might see them come up. We want to be able to do problems where we classify a salt that I give you as neutral, acidic, or basic. And so here's an example, cesium perchlorate. When you're doing an example like this, you have to look at each ion individually. So you have to say, what kind of an ion is cesium? What kind is perchlorate? And then put the two effects together. Cesium is one of the ions that's in group 1, along with sodium and potassium, so it's neutral. And perchlorate, it comes from a strong acid, HClO4, and so that would be classified as neutral also. So if you have two neutral ions, there's nothing to change the pH, and so you'll also get a neutral salt. KClO2, if you wanted to classify that one, you have to look at the ions separately again. K, of course, is neutral because it's in group 1. ClO2 is actually a basic anion because it's on the right of the arrows in the Ka table. And this is showing it. So if you put together a neutral and a basic, you get a basic salt. In order to do ammonium iodide, you look at the fact that ammonium is the acidic cation. Iodide comes from a strong acid and is therefore neutral. So if you put an acidic together with a neutral, you get an acidic salt. I not only want to classify these salts, but I also want to calculate the pH of them. The thing is, it's the same problem we did in the last lecture with just a little bit of an extra thing. Let's suppose I ask you to calculate the pH of 0.08 molar KNO2. Before we do this, we have to classify that as, well, first of all, a salt, because it's a positive and negative ion together, and we have to decide whether it's acidic, basic, or neutral salt. Since NO2 is on the right of the arrows here, it's a basic anion. But since sodium is in group 1, it's neutral, and so neutral plus basic gives you a basic salt. To calculate the pH of it, you can consider potassium to be a spectator because it's not going to affect the pH. So what this actually is the same as calculating the pH of 0.08 molar NO2 minus ion. These are ones we did in the last class because NO2 minus is a weak base, and so you need to do a weak base pH problem. These are the problems that have 2 extra steps over and above an acid problem. If you write the ICE table, it looks just like they did last time. The thing is, you have to write, because this is a base, you have to write a Kb and not a Ka. The way I showed how to do that last time, I always put this in that dashed box. You have to take 1 times 10 to the minus 14 divided by the Ka in order to get the Kb, and that's what you set the fraction equal to. So if you want to solve that equation, you do it the same way as always. Multiply both sides, take the square root, and you get x. And because this is a base problem, x equals OH. In a base problem, since it's OH, when you take minus the log, you actually get the POH, so you also have to do the 14 minus step at the end. So this is a review of the fact that a weak base problem has 2 extra steps. You first of all have to get the Kb from using the 1 times 10 to the minus 14 divided by the Ka, and then at the end of the problem you also have to do the 14 minus step. This problem is asking you to calculate the pH of ammonium bromide, 0.08 molar. We're going to have to classify this salt also. Everyone knows that ammonium is the acidic cation because it's on the left of the arrows in the Ka table. Bromide is neutral because it comes from a strong acid, HBr, and if you put acidic plus neutral, you get an acidic salt. Because the Br minus does not affect the pH, you can consider it a spectator, and so this is exactly the same problem as calculating the pH of 0.08 molar ammonium, which is a weak acid that we did last time. Here's the ice table, and you can write the Ka this time and use the number directly from the table because it's an acid. We don't have to convert it to Kb. When you solve for x, the x is actually equal to H plus because this is an acid, so when you take minus the log, you get the pH directly. I want to tie up a couple of loose ends at this point, and one of them is I want to make sure that everybody is completely familiar with what you need to know about molarity. We've already calculated molarities where you take moles per liter. If you rearrange this equation mathematically, you can solve for moles and then convert it to grams if you need to, and you can also solve for liters and convert it to ml if you want to. I wanted to give you some example problems of this, and so I show them in the next couple slides. We already did this problem during the first lecture where you calculate the molarity from grams and milliliters. This is an example of a problem where you calculate moles and then grams from given the molarity and the liters. This is an example of one where you calculate liters given moles and molarity. We're going to use all three forms of this equation in the next couple days, and I just want to make sure that everybody is thoroughly familiar with these problems and you're able to do them so we can use them in the next couple lectures. I also have one other topic that I want to do with electrolytes. I showed you this picture in an earlier class, and you know, first of all, that electricity has to travel through a complete circuit. If you put those two electrodes into a non-electrolyte, they will not conduct electricity. But if you put them in a strong electrolyte, like at the bottom of the page, they will conduct electricity very well. We haven't talked about weak electrolytes very much, but now that we've done weak acids, we can talk about that. And weak acids are the main type of weak electrolyte. We're also going to show that ammonia, the neutral weak base, is also a weak electrolyte because it only ionizes to a small extent. And if you remember these pictures, I showed that when you put those electrodes in pure water, they do not light this light bulb. When the person put the electrodes in a strong acid, hydrochloric acid, he got a very strong light. When you put them in a weak acid, acetic acid, he just got a dim light. That's the reason why they call acetic acid a weak electrolyte. You should be able to describe a substance as a strong, weak, or non-electrolyte by using this classification, but you really already know it because we've already gone over it. I just want to formalize it that strong electrolytes are anything that gives you 100% ions, strong acids, strong bases, and salts that dissolve. Non-electrolytes are, first of all, pure water, but then I asked you to remember sugar and alcohol as representatives of covalent compounds, and weak electrolytes, weak acids, and also we're going to describe that the weak base NH3 is a weak electrolyte. The one problem in this scheme is that even though a lot of the negative ions that are on the right of the arrows in the Ka table are bases, weak bases, compounds that have those in them are not classified as weak electrolytes, and I'm going to show you why. It's only the neutral weak base ammonia that's actually called a weak electrolyte. If we practice classifying using this scheme, as soon as you get to what it is, there's no overlap. As soon as you find one, that's what it is. So for HClO4, it's a strong acid, which also means it must be a strong electrolyte. Ammonia is the neutral weak base, only ionizes a few percent, and so it's also called a weak electrolyte. And HF, Homewood Flossmoor, is that what it is? Hydrofluoric acid. It's a weak acid because it's not one of the six. Since it's a weak acid, it's also considered a weak electrolyte. The two here at the top of the page, you're not supposed to know what alcohols and sugars have formulas that look like whatever yet, And so I have to tell you it's an alcohol or a sugar. So if I tell you that, obviously they're not electrolytes. Now here's the one that's a problem. Potassium cyanide contains Cn-, and it is true that Cn- is a weak base because it is on the right of the arrows in the Ka table. The reason why KCN, though, is not considered a weak electrolyte is that Cn- does make extra OH ions when you put it in water, but that doesn't have any influence on whether a substance is actually an electrolyte or not. If you dissolve KCN in water, you are going to get 100% ions because K makes everything soluble. That automatically makes it a strong electrolyte. Doesn't matter whether the salt is acidic, basic, or neutral, it is a strong electrolyte because of the number of ions. If you're doing pH problems, that's like the next step down. Cn- would give you OHs, but that really doesn't have that much to do with the electrolyte properties. That has to do with pH. You can see here that sodium sulfate is a soluble salt, and so all soluble salts, no matter what they are strong electrolytes because they make 100% ions. Now if you look at the next two, sodium hydroxide and strontium hydroxide, those are strong bases, and they also dissolve in water, and of course strong bases give you 100% ions, so they are also strong electrolytes. The last one on the page is formic acid, and you might not be familiar with it right away, but we're going to use it in buffers, and it is a weak acid because you can find it in your table. So since it's a weak acid, it's also a weak electrolyte. That's what I wanted to cover about salts and electrolytes. Now the next topic we're going to cover, though, is different, and I want to discuss why we're going to discuss that next. We are going to get into the third major kind of reaction that we're going to look at in Chem 132. In the first part of class, we looked at precipitation reactions and acid-base reactions and pH. Now we're going to talk about redox. The reason why we want to do this is because redox reactions are very important in chemistry in general. Not all reactions are redox. The main kind of reaction that's not redox is double displacements, and that does cover both precipitations and acid-base reactions. There is no transfer of electrons when you do either one of those kinds of reactions, and so titrations and buffers and precipitates, none of that has any relation to redox. But redox reactions are very important, probably at least maybe a third to a half of them in industry and organic are redox. So let's just an estimate, but we need to talk about them. And one of the main reasons is that in this class, our topic is not going to be primarily balancing redox equations. It's going to be how you use redox equations for balancing or for making batteries. All the portable batteries that you use in your cell phone, laptop, all the rechargeable ones, even the AA and AAA that are not rechargeable, are all based on redox reactions occurring inside the battery. There's a huge field of studying these batteries because they're so important, and we need to study first the reactions, but the main topic we're going to cover is how you make the batteries from a redox reaction. For that reason, I want to tell you that a lot of people are afraid of balancing redox reactions because it is somewhat of an ordeal to go through all those steps in Chem 131. I made the decision that I am not going to teach the 131 method completely in this class because we need to study voltages, which is the main property of a battery. In order to get voltages, we have to have a table of half reactions. And so I'm going to let you balance using tables because that's how you look up voltages, and that's what we want to focus on. We do have to be able to balance equations, but the thing about balancing is that it is much, much easier to do when you have tables of half reactions to use. You remember in 131, if you're balancing redox, you have to add H plus on one side to balance the H's, water on the other side. Then you have to add electrons. You have to equalize the electrons, cross them out, and add. If you're going to basic conditions, you have to add the same number of OH's on each side that you had H pluses and cancel the extra water. If your 131 teacher did not show you how to do that method, they are not doing their job, because that is a required part of the American Chemical Society system for teaching chemistry. The thing is, even if they didn't teach you, you're going to be able to do it by the method I show you in this class, because you don't even have to be a chemistry person to be able to balance. All you have to do is be able to recognize things in the reactions, turn the correct reaction around, equalize the electrons through the least common multiple, and then add. So I want you to relax about balancing, because it's not going to be the ordeal that it was in 131. And if you are able to know that, we can concentrate on what we're going to study about batteries. Now I have to discuss these terms that are related to redox, and these are leftovers from the 1800s and early 1900s. The truth of it is, you could get rid of all these crazy terms if they would just use the Mark Churchill system. And that is, you call everything in a redox equation either an electron gainer or an electron loser. If you did that, all this other stuff would not be necessary. The thing is, none of this is going to disappear because it's been around for so long, so we have to deal with it. The thing is, I want to show you that these terms actually make sense, first of all. That's really important to believe, and there's a reason why they use the words. And I also want to relate everything to loser and gainer, because that's what you really need in organic. There's a lot of redox reactions, and also in analytical chemistry and physical chemistry if you're a biochem or physics major, or chemistry major. And so I'm going to try to show you what these terms actually mean and illustrate them. The first term here is called oxidation number, because a redox reaction is defined as a reaction where you transfer electrons from one substance to another. If the reaction does not transfer electrons, it is not redox. But if it is redox, you have to have a way of keeping track of the way the electrons are going. The oxidation number for monatomic ions like Na plus and Cl minus, I don't see any difference between that and the charge. I mean, if you take an electron away from a sodium, you're going to get an Na plus. And if you add one to a chlorine, you're going to get Cl minus. There are chemistry teachers who would crucify me for saying that, because they're trying to tell me that, no, these are not the same thing. Oxidation number is a theoretical principle, and charge is an actual thing from the lab, and you have to write one of them +2 and the other one 2+. And I just am not that picky because of one simple reason. I don't get it. I do not understand what they're talking about. So if I don't get it, you don't have to get it. We're going to call charge and oxidation number the same thing for monatomic ions. The problem comes in if you want to try to calculate an oxidation number for a covalent substance, because covalent substances do not have charges. And you really do have to define a way to do that because there is no obvious way. And the oxidation numbers that you calculate in covalent compounds are not real charges. They are an experimental or theoretical construct that you use for a lot of beneficial purposes. I just want to first of all talk about some of the terms that are related to redox, and we're going to get into covalent oxidation numbers in a minute. I think you probably heard these terms before, that oxidation is loss and reduction is gain. The thing is that how do you remember this? Well, I'm supposed to teach you this from first principles, whatever that is, but I'm not going to do that because I think it's a lot easier to learn these from anybody that starts a word with MN ought to be shot. Mnemonic devices, and here they are. Leo Gur. Leo's a lion. Lions go grr. That's loss of electrons is oxidation, gain of electrons is reduction. You can also use oil rig. Oxidation is loss, reduction is gain. I don't care how you remember this, as long as you remember it. The problem comes in when you talk about agents. And these terms can be confusing to people. What is an oxidizing agent? Well, an agent in chemistry is something that causes a result. For example, a real estate agent is a person that causes you to buy a house. A movie agent is a person that causes an actor to get a job. So agents cause something. Oxidizing agent is a substance that's going to cause oxidation. Now, if you cause oxidation, oxidation is loss. So you have to cause the loss of electrons on the part of something else. How do you cause something to lose electrons? You take them. That's the reason why oxidizing agents are the gainers. These are the ones that gain electrons, and I put this in a box because this is probably the most important use of the terms that chemists use. A reducing agent has to cause reduction. How do you cause someone to gain something? You have to give it to them. And so reducing agents give electrons to other substances, and therefore reducing agents are the losers. I want to show this with a specific example of a reaction. If you take the element sodium, which has one valence electron, what that means is you know that sodium wants to lose an electron so that it gets to be like the nearest noble gas that has an octet around it, and that would be neon. So if sodium loses an electron, it gets the same electron configuration as neon. Chlorine, on the other hand, is a diatomic element. The electrons are shared, but it wants to gain one electron because it wants to be like the nearest noble gas, argon. So chlorine has to gain one electron in order to be able to make an octet, and then it has a negative charge. If you take the element sodium and put it together with the element chlorine, the sodium is going to transfer an electron to chlorine, and then they're both charged, but they're both also relaxed, and they can make the compound sodium chloride. Now, the thing I want to point out is, do you know what the element sodium is like? It is an extremely reactive metal. It's soft. You can cut it with a knife. If you leave it sit out in the air, it will eventually explode because it reacts with the water in the air. And if you tried to swallow some, it would probably release hydrogen gas in your stomach, and that means if you burped and lit a match, you could be a dragon. Sodium is a very dangerous substance. Chlorine gas is poison gas. It was used as poison gas in World War I, and it was really horrible to breathe that stuff in. It destroyed your lungs. And so, how can you take two horrible substances like that, mix them together, and end up with table salt? I want to show you that this is the reason why any redox reaction happens. And in the next slide, someone was crazy enough to take sodium and put it in water in front of a bunch of people that sound like junior high students. So let me show you what happens when you put sodium in water.
Sodium metal in. So that's fire on top of water there. Little orange flame there. It's a ball here, you'll notice. It's a round shape there. And that's because it's it has melted, and so that's actually molten metal there rolling around the surface. And notice it's all gone there when it's all reacting. So more.
The next slide is going to show someone doing the reaction between sodium metal, the solid, and chlorine gas. In other words, the two elements. Chlorine gas is actually a greenish yellow colored gas that you'll see in the flask in the next slide.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
Now, what is that white stuff in the flask after that reaction? Well, the white stuff is sodium chloride. That's the product of the reaction. And I think there's also a little lump of it down at the bottom of the flask there, if you look closely. How could those two dramatically dangerous substances make sodium chloride? Well, the reason is that when sodium wants to lose the valence electron, it is extremely adamant about it. I mean, it really wants to get rid of it. When chlorine wants to gain an electron, it is really, really wanting to do that. So when sodium and chlorine come together, the sodium shoots an electron over to chlorine, and when that happens, they both completely relax because they are now happy. Their electrons are both an octet, and that's why sodium chloride is not dangerous and it's edible, because the two ions are completely happy once they've traded the electron. Now, if you look at the oxidation numbers, we're going to call sodium and chlorine an oxidation number of 0 because that's true for all elements. They haven't done anything yet. It's when they react, the sodium loses an electron, so it becomes +1, and the chlorine gains 1, so it's -1. Those are the oxidation numbers of those elements in sodium chloride. You can tell what happened in the reaction by looking at what happened to the oxidation numbers. Sodium went from 0 on the left to +1. On the right, that's up. And chlorine went from 0 on the left to -1 on the right, that's down. Whichever substance goes up in oxidation number has lost electrons, just like sodium, and loss of electrons is oxidation, so it's called oxidized. The reason why they use that word is it means as if it was treated with oxygen. Um, Oxygen is the second best substance on the periodic table at gaining electrons. Fluorine is number one. Fluorine is so reactive that they didn't even isolate it till the 1950s. All the containers that they tried to isolate it in got chewed up by the gas and they turned into HF. They finally discovered Teflon, which is completely fluorinated, and so fluorine can't react with it, and so you can collect fluorine gas in a Teflon container. The thing is that before that time, for many years, oxygen was the best element known that could take electrons away, and so they used the word oxidized. Now the chlorine went down in oxidation number. That means it gained electrons, and they used the word reduced. What was reduced? Well, the oxidation number. So I don't know if that's a good term, but that's the reason they use the word reduced. The oxidation number went down, and so these are the way the terms are used. If you want to look at the terms agents, these are more confusing, but if you look at them, they're not bad. Why do they call sodium the reducing agent? Remember that a reducing agent causes something to be reduced, and reduction is gain. So that means sodium caused the chlorine to be reduced, and therefore the sodium is the reducing agent. The chlorine is the oxidizing agent because it caused sodium to lose electrons or be oxidized. The reason why people are confused by this is they say that the way it's worded, oxidized and reducing agents sound like the opposite. But to a chemist, they're not opposite at all. The word oxidized means lost. Reducing agent means causing something else to gain electrons by losing. So oxidized and reducing agent both mean loser. On the other side, the reduced means that the thing gained electrons. Oxidizing agent also means that it gained electrons. So both of those terms mean that substance is the gainer. Since you try to determine what the reaction is doing by calculating oxidation numbers, I want to show you how to do that for covalent substances. See, for monatomic ions, oxidation number is really the same as the charge. But in covalent substances, there are no charges. Electrons are still shared. So what you have to do if you want to define oxidation numbers in a covalent compound is you have to make a definition for how you want to do it. The reason why they want to do this is because even though these are not real charges, they help you do all kinds of things. They help you balance redox equations. They help determine which way the electrons go. For example, in the wire in a DC electrochemical cell. And in organic, they do things like telling you whether the electrons in a substance move from one thing to the other along with the atom that's moving, or do they stay behind and the atom moves by itself to the other substance. There's all kinds of reasons why you want oxidation numbers for covalent substances. So in order to do this, chemists have defined what's called an assignment technique. The rule is that if you want to get an oxidation number for covalent stuff, there's always a bond between the two atoms where the electrons are shared, but one of the two atoms will always be more electronegative than the other. If you remember what that term means, electronegative means if you're more electronegative, you attract electrons better. And so the one with the higher electronegativity is the one that you are going to assign the electrons in the bond to because they're already closer to that atom. This is not real. It's an assignment technique. It's not a real charge, but you do it mentally. And after you've done it, you then determine what the charges would be. Those are what are called the oxidation numbers. If you remember this scale, fluorine has the highest electronegativity, which is 4.0, and the electronegativities decrease as you go down, and they also decrease towards the left. And the metals have very low electronegativity values because they don't want to gain electrons, they want to lose them. I'm going to use the example of sodium sulfate to show you how this works in covalent substances. Sodium sulfate is very definitely an ionic compound because sodium is positive and it attracts to the negative sulfate. But if you remember, the bonds within a polyatomic ion between the sulfur and the oxygen are actually covalent. And so you need to assign oxidation numbers to the sulfur and the oxygen. Because it's covalent, somebody might have asked you to draw the Lewis structure of sulfate when you were in 131. So that picture's on the next page. Sulfate has 4 single bonds. Even though some books try to put double bonds in, that's ridiculous. There's maybe 10% resonance, that's all. They're single bonds. And so what you're going to do is try to get oxidation numbers for each atom. The -2 for the whole ion is not an oxidation number. That is what's called an overall charge. That's the charge of all the ion put together. All 5 of the ions together have gained 2 electrons. Oxidation numbers are not overall charges. They are numbers that are assigned to individual atoms. Each atom has its own oxidation number. In order to do that, you can look up the electronegativities of sulfur and oxygen in the periodic table, and that's where you start. So since the oxygen is 3.5 and the sulfur is 2.5, oxygen attracts electrons better, and so you mentally take both of the electrons in each of those bonds and give them to oxygen. If you do that, the oxygen is now going to have 8 electrons, and it starts out in group 6. So it's originally at 6, it gained 2, and so each oxygen is -2. The sulfur also starts out in group 6, but it lost all the electrons, and so now it is +6. These are what are called oxidation numbers. They're not real charges. You'll never find a +6 sulfur anywhere. It's just an oxidation number in a covalent compound to use for different purposes. Because of the fact that you did not gain any electrons or throw any away, you just rearranged them. If you add up the oxidation numbers, they have to come out to the charge of the ion, the overall charge, and you can see that they do. So the sum of the oxidation numbers in an ion has to equal the charge of the ion. If you look at a complete compound like sodium sulfate, this compound is neutral, so you could put a +1 above the sodium, a +6 above the sulfur, and a -2 above the oxygen. Notice that I did not put a +2 above the sodium or a -8 above the oxygen because oxidation numbers are for individual atoms. But if you add all the oxidation numbers, they have to add up to 0 because this is a neutral compound. And if you look at the calculation, they do add up to 0. So that means that the sum of the oxidation numbers in a neutral compound equals 0. You are going to determine oxidation numbers not by drawing Lewis structures, but by rules. These are the same rules that most people use in Chem 131. And so we already know 6 of them, and we just have to talk about 1 and how to get the rest of the oxidation numbers. So let me talk about these. First of all, elements are all 0 because elements are neutral and they haven't done anything yet, and that includes diatomic elements. Metals in compounds are always positive. You already learned a lot of the charges for the group 1 2 and 3, +1, +2, +3, and also for some of the transition metals and the ones at the bottom of the groups. Metals can never be negative. They can only lose electrons, not gain them. These are some of the charges you already learned, and you can see that all the metals are positive. The negative charges that you learned for the nonmetals and metalloids, group 7 is -1, 6 is -2, etc. Those are when the nonmetal or metalloid is actually combined with a metal, because the metal is positive, or with hydrogen in an acid. These are the normal charges that you usually see, and these are the ones you learned the pattern for in the periodic table. You can see the -1, -2, and -3 listed on the right of the table. The only time when nonmetals and metalloids get those goofy positive charges is when oxygen is present, and also fluorine, but we don't have that much fluorine. See, oxygen is stronger than all of them, and so it pulls electrons away from them. That's when you get things like a +6 sulfur. I want you to know that when you're looking at a periodic table, you can think of nonmetals and metalloids as pretty much doing the same thing, because the fact of the matter is that chemists think of metalloids more like nonmetals, because metalloids act much more like nonmetals in chemistry than they do metals. They have some properties that are like metals physically, but chemically they're like nonmetals. The only one that's not, as we said, is aluminum, because that one's a metal. We already talked about 5 and 6, which are that the sum of the oxidation numbers in an ion equals the charge of the ion, and the sum in a neutral compound equals 0. Rule 4 is the one I want to talk about, because this is where you start calculating oxidation numbers in compounds. I put in that fluorine is -1. Nothing can take electrons away from fluorine, even oxygen, but we don't usually use fluorine that much. By far, the two most important ones for us are the ones in boxes here, that oxygen is almost always -2. Why is that? Oxygen is the second strongest. It wants 2 electrons, and therefore it gets them. Hydrogen is almost always +1. And because that's an acid, right? H+, it loses. I want to tell you that there is an ion for hydrogen that is an exception that I'm not going to ask you to know. It's called hydride. It's where hydrogen gains an electron and becomes like the noble gas neon. It's a negative ion, but the thing is, it's a very unstable ion because there's only one proton trying to hold 2 electrons, and it's very, very reactive. You're going to study a lot of hydride. If you take organic chemistry, there's hydride shifts, and there's reagents that are made specifically to add H- to organic compounds. So I'm going to leave the hydride for organic. We're going to only have H pluses being RHs in this class. There is a particular exception for oxygen, though, that I have to discuss because it's so important in chemistry and physiology. In the ion peroxide, and I showed the structure of hydrogen peroxide at the bottom of the table here. The reason why oxygen is -1 in peroxide is that there's 2 oxygens connected to each other. So when you distribute the electrons, you can't give both of them to either oxygen. You have to give each oxygen one of them. So oxygen starts out with 6, and it's now 7. So it's a charge of -1. But peroxide is one of those ions that always goes in pairs. It's like mercury 1. You always see O2, 2-. See, the regular oxygen by itself is O2 minus. That one's called oxide, but the oxygens in peroxide are the ones that are always together, and each one is -1. You don't have to be able to detect which ions are peroxide, because I will tell you if a compound is a peroxide. The thing is, I do want you to know that exception, H2O2. The reason why I want to talk about peroxide, though, is because it's such a versatile thing in, first of all, chemistry. It's a weak acid, first of all, and secondly, it can be either an oxidizing or a reducing agent in chemical reactions. If we were doing the qualitative analysis lab, which is the one we do when we're face-to-face, peroxide is used in many steps in those labs. And the other thing is that in physiology, peroxide is the beginning of a cascade that is called active oxygen species. When a white blood cell phagocytizes a bacteria, for example, how does it kill the bacteria? First of all, it dumps lysosomes on it, and those have enzymes that digest proteins, proteolytic enzymes. But there's also an organelle in white blood cells called a peroxisome, and the purpose of them is to generate lots of peroxide and to dump those species all over the bacteria to kill it, to chews it up. But peroxide is not as reactive as some of the later oxygen species, like things that are called like singlet oxygen and hydroxyl radical. That's a hydroxyl radical is a free radical, and if you study biology, you know that those are the cause of primarily aging and cancer. But anyway, they can cause that. But they dump all these active oxygen species on the bacteria, and it chews them up. But it also kills the white blood cell, and then all of that stuff from inside the cell leaks out, and it starts to digest your own tissues. That's what's called inflammation. After the bacteria is gone, your body comes back and remodels the tissue, but the active oxygen species that hydrogen peroxide starts are a very important topic of study in biochem, and I'm sure if you take a biochem class, you're going to spend quite a bit of time on those because of their importance. Because these two in the box are the most important, though, when you're calculating an oxidation number, as I'm going to show you in the next few examples, you do it by starting by putting a -2 above all the oxygens, a +1 above all the hydrogens, and everything else is a variable. Let's say I wanted you to calculate the oxidation numbers in BiO3-. In order to do this, you're going to start by doing what we just said. You're going to put a -2 above the oxygen. There are no hydrogens to put a +1 on top of. And then you're going to leave bismuth as the variable x. You know that the entire thing has to add up to -1 because that's the charge. So if you put in the x plus 3 times -2 for the 3 oxygens, it all adds up to -1. And if you get an oxidation number then for bismuth, by solving for x, it comes out to +5. This is the memory ion dichromate, and so if you were going to do this one, put a -2 above the oxygen and an x above the chromium, but this time you have 2 chromiums, so you're going to have to make it 2x. The whole thing has to add up to the charge -2, so you're going to end up with 2x plus 7 times -2 equals -2. So if you solve this for x, it shows that the chromiums are +6 and the oxygen is -2. It's of interest that the chromium +6 is what's called hexavalent chromium. That is one very important environmental toxin that gets into public water systems sometimes. So if you're do anything with toxicology, you're going to probably see hexavalent chromium. This is nitric acid. And so we're going to when we put the numbers above it, you put a -2 above the oxygen and a +1 above the hydrogen. Don't forget about hydrogen, and then the N is a variable. The whole thing has to add up to 0 because nitric acid is neutral. If you add everything, the +1 plus X and 3 -2's, and then you solve, you get a +5 for X, and that's the charge of the that's the oxidation number of the nitrogen. This is a complete compound, and I want to show you one extra thing you sometimes have to do to get oxidation numbers. Iron carbonate, you are going to start the regular way. You put an X above the carbon and a -2 above the oxygen, but it looks like you might have two variables because what is the charge of iron? But it's not a variable because you can get it by uncrossing. Sometimes you need to do that. If you uncross to get the charge of iron, it shows you that the iron is the +3. Now, when you're doing this, you have to be very careful of how many atoms there are. There's 2 iron, but please don't forget that there are 3 carbons because the 3 is outside, and there are 9 oxygens. And the whole thing has to add up to 0 because the compound is neutral. So you got the 2 plus 3 irons, 3X for carbon, and 9 times -2 for the oxygen. If you solve that equation correctly for X, you can see the steps there. You get that the carbon, or X, is +4. And so carbon is often +4, and here it is. This is an example. The question this one asks is the carbon going to be the same without the iron present? And the answer is yes. Let's see why. If you put a -2 on the oxygen, the whole thing has to add up to -2. So when you plug them in and set the whole thing equal to -2, you can plug in and find out that the carbon is +4 again. The concept here is that whether there's an ion with a polyatomic ion or not, the precipitation part, or the combining of the 2 ions together, is a double displacement, and that is not redox. The truth is that polyatomic ions have the same oxidation number of the central atom, like carbon, no matter what's attached to it. So for example, SO3 2- has a +4 sulfur, SO4 2- has a +6 sulfur, doesn't matter what's attached to it. And so that's an important part of determining the properties of what the polyatomic ion is going to do by knowing the oxidation number of the central atom in it. Now, next period, what we're going to do is we're going to take this information about oxidation numbers in redox, and I'm going to show you how you actually construct an electrochemical cell. And you are actually going to construct an electrochemical cell in the final experiment you do in the lab here. You're going to actually make a battery. We're going to show how to do that. And if you're familiar with how to use those terms I showed you, and you know how to calculate oxidation numbers, you are ready for the next class, which is making batteries. And then in the second half of that class, we're going to balance redox. And I'm going to show you how to do it from the tables, which is a much easier process. So we'll do that next time.